All right, so here we are finally in Unit 8. We're finally talking about chemical reactions, what goes into it, what's happening, what's changing. So to get that all started, let's talk about chemical equations. These are the ways that we will be writing out chemical reactions to make sense of what is going on. So overall in this section, we will go over chemical reactions, how that's different from chemical equations. We'll explain what the law of conservation of mass is, and then we'll go over how to balance a chemical equation when it is not balanced. So if you remember back to Unit 2, that's when we first started talking about properties. We took different properties and we categorized them as either physical properties or chemical properties. And then later in Unit 5, we started to move away from just using elements and actually combining different elements into compounds. And we know what holds compounds together are chemical bonds. So now when we have a chemical reaction, this is something that involves either the breaking of bonds or making new bonds between atoms. Now, the way that we can write this down and to keep track of what's going on is that we use a chemical equation by using symbols, and this represents the chemical changes that we see in a reaction. So the way to write this very generally is that we have two sides to a chemical equation. On the left side, we start with the reactants. These are the things that go into a chemical reaction and will go through some form of change. This arrow in the middle means that your reactants are working together and they're changing to create a new product. And these products will be different from the reactants that we started with. And so if you can think of this in a time-wise fashion, you can think of sort of the left side as being the before and the right side being the after. Again, this is what you start with, the reactants, and you end with new products. So it's just the general format for chemical equations. So let's actually look at a specific example and see some of the parts that go into it. So this is what a chemical equation would look like. And so here's what's going on. So notice that here on the left side, I have more than one thing. I have two different compounds. I have C2H2 and I have O2. And these two are reacting together to form a change and they become different new products on the right side, where we have CO2 and H2O. And so it's important to note on these that these compounds, all these elements that we have bonded together, these will be the chemical formulas of our chemical equation. And what's important here is that notice that there's these numbers that go with them. Here we have CO2 to tell us how many atoms are in that compound. Here we have H2O, and it tells us again how many atoms are in a compound. And in these chemical equations, we also have a different set of numbers. Notice that these numbers go in front of the compounds that we're dealing with. And these are a little bit different. These are called the coefficients. And actually, these coefficients represent the number of moles of each compound or element that we can have. So what's important on this is that the coefficients that are part of the chemical formulas, these do not change, because when you change these coefficients, no, not the coefficients, when you change the subscripts of the chemical formulas, this will change the compound that you're working with. So in this one, if you were to change, the carbon dioxide with two oxygens, if you were to take one of those oxygens away, you would have carbon monoxide, which has very different properties than carbon dioxide. Carbon dioxide, it's a byproduct of cellular respiration. You breathe in oxygen, you breathe out carbon dioxide. So it's very common, but carbon monoxide, on the other hand, with only one oxygen, that's a poisonous gas. And so you know that we don't breathe out a very strong poison like carbon monoxide is. And then same thing for H2O. If you were to just add one more oxygen, you'd have H2O2. That's not water anymore. That's now hydrogen peroxide, which can be poisonous as well. All right, and so that's different from the coefficients, because as you'll be seeing, to balance chemical equations, we can change the coefficients. They can change, they don't necessarily have to change, but these coefficients are just showing the number of moles of each compound that we use. So again, more on that for the balancing chemical equations. So let's talk about this, the law of conservation of mass, because it's actually a very important concept, because this law of conservation of mass is one of the laws that govern all of nature. So just put very simply, it just states that mass cannot be created nor destroyed. It always has to come from somewhere, and we can't lose it in the process of whatever it is that we're doing. And so the way that, again, it's just a restatement, is that it can only be changed or transformed. We can't make new matter, and we can't get rid of it. And so, just something that I need to clear up right now is that the way that we'll be talking about this law of conservation of mass is really just a simplification of what the way it actually works. Because when we are doing our chemical reactions, if you follow the law of conservation of mass, is that if you put in 10 grams of a reactant, you should be getting 10 grams of a product out. But in reality, sometimes you lose a little bit of that mass. You might get 9.8 grams of your products out. And so we haven't violated any laws. What's actually happening here is that some of the mass that we started with gets converted into energy. And, it was thanks to work of scientists like here Albert Einstein that they came up with this equation, the very famous equation that is E is equal to mc squared, where actually it relates energy and mass together. And so that, using this equation, explains where the missing mass goes to. It just gets converted into energy. But like I said, is that we're just going to simplify it down. It gets a little bit more complicated when we try to factor in the energy of a system. So for that reason, we're just going to ignore it. So I just wanted to bring this up, that it's still there, but we're not going to be talking about it, just to keep it simple. So the only thing that we need to focus on is that when we're doing chemical reactions and chemical equations, we're simply rearranging the atoms that are involved in our equation. So that means that we start with a certain number of atoms and we end with that same number of atoms. And this finally brings us to balancing chemical equations. So again, coming back from the last slide, is that we stated the law of conservation of mass means that we cannot create or destroy mass. It always has to come from somewhere, and we always need to keep it around. All right, so for our chemical reactions, what that means is that what we put in is exactly what we get out. And so our reactants and our products must have the same number of atoms on each side of the reaction. And when I'm talking about same number of atoms, I'm not just talking about put in 10 atoms, get out 10 atoms, but we also have to focus on the specific type of atoms. We need to focus on the elements and how many atoms of each we have. So let's go ahead and look at an example here. So it's a lot like the reaction or equation that we saw before, but there's something missing. We need to go through and find out if this is a balanced equation, if it abides by the law of conservation of mass. Now, when we're doing this process, keep in mind these steps, that when we balance a chemical equation, the first thing you need to do is count for every atom on both sides of the equation. And like I just said, is that it's not just, the total number of atoms, but I need to focus on each type of element and how many atoms of each there are. So when you're doing this first step, it's useful to write out a list of all the elements that you have in that same reaction. So again, we have the reactant side on the left, we have the product side on the right, and then we need to go through and count for all the atoms. So if we just start here with the first one, carbon, notice that there's C2. This means that I have 2 carbon atoms in the equation. So if we follow right along, hydrogen comes next. There's 2 hydrogens, so I'll go ahead and say that as well, 2 hydrogens. And finally move on to the next reactant. I have O2, so that means that I have 2 oxygen atoms. Pretty straightforward. I have all 2's on these, but this doesn't really mean anything yet. I need to count for and compare to the product side. So I'll just do that same process, do it again on the right side of the equation. So again, I can find that carbon on here, so there's only 1 carbon written down for me. So I only have 1 carbon on the product side. Moving right along, hydrogen here, there's only 2 hydrogens, so I'll save that 2 hydrogen. And then finally for oxygen, that's where it gets a little bit more interesting, because there's 2 compounds on the product side with oxygen. So here I have O2 and a single O on the second compound. So again, 2 plus 1, that means that I have 3 total. All right, so now that I have a full list of all the elements that I have on both sides of the reaction, I can go through and compare them. And you can see that if you focus on hydrogen, 2 on the left, 2 on the right, so that's okay, that's great. But notice that carbon and oxygen give me a little bit of a trouble on this one, where my numbers of carbon from left to right are not the same, and oxygen on the left and on the right are not the same. So we need to do something to fix those, and this is where we can work on step number 2. We can take the different coefficients of each compound and we can raise them. We can never lower our coefficients, but we can always raise them to try and match things. All right, and so remember that the coefficients are the numbers that go in front of the compounds. They're not the subscripts that go along with the individual elements. So remember, those subscripts you cannot change. The coefficients that go in front of each compound do change. So let's go ahead and see an example of that. So again, I said that coefficients can only increase. So if we look to our first example on carbon, here I have 2 on the left, 1 on the right. Because I have less atoms on the right, I want to start raising that one. So I need to find my compound that has the carbon on the right side. Here it is, CO2, and I need to start raising it. The way that we're going to do this is just going to be a lot of trial and error. We're going to put something down, change coefficient, and see how that affects our chemical reaction. All right, so if I start with that, there was only an implied 1 for my CO2, so I need to raise that to the next number. I will go with 2 moles of CO2. So here I need to apply this 2 coefficient to every atom that comes after it. So this one 2 will apply to the carbon. So really my carbon goes from 1 and that changes to a count of 2. But this coefficient also applies to the oxygen that comes after it too. So in this case, I had 2 oxygens that I'm, in this case, multiplying by 2. So my oxygen count will also change. So 2 times 2 oxygen, that's 4, plus 1 from the water molecule. So in total, I'm going to 5 oxygen atoms. And so again, this takes care of my carbon to carbon. They're finally matching, but my oxygens are still not matching. I have 2 on the left and 5 on the right. So I still need to keep working on this to get it to balance out. So one thing to point out on this one is that notice that on the left side, I have a molecule of O2, which means that if I were to raise the subscript on this one is that the total amount of oxygen on my left side will always go up by an even number. And so that doesn't match up with this H2O molecule, which only has a single oxygen. So I need to go through and make this this water molecule give me an even number of oxygen. So to do that, I will add a coefficient of 2 in front of the water molecule. And again, that's going to change my count for the hydrogen atoms and the oxygen atoms. Let's start with oxygen. This 2 is multiplied by 1 oxygen atom, so that gives me 2 oxygen atoms, and then counting the same ones from the carbon dioxide molecule and the water together, that's 4 plus 2 gives me a total of 6 oxygen atoms on this right side. So now I've changed my number of oxygen atoms. I also need to change the number of hydrogen atoms after I added this latest coefficient. So now 2 times 2 hydrogen atoms will give me 4 hydrogen atoms. All right, so now taking a new comparison between these atoms. Again, carbon is all balanced out, 2 on the left, 2 on the right, but now hydrogen, 2 and 4, it's not matching. 2 and 6, oxygen are not matching either. So I still need to keep working through this. So now let's see what's out of balance on this one. So let's see, I have more hydrogen on the right side than I do on the left. So I need to raise my number of hydrogen on the left side. So here's my hydrogen compound on this one. It is C2H2, and I have an implied 1 coefficient in front. I need to raise it to the next level. Let's make it 2. So when I do that, the 2 applies to 2 hydrogen atoms. 2 times 2 will now give me 4 hydrogen atoms. And remember that this coefficient 2 also applies to the carbon. So I need to recount for my carbon now. So 2 times 2 carbon will give me a total of 4 carbon. So now after doing that, my hydrogens are finally in balance and they match from the left side to the right side, but now my carbons aren't matching anymore. So now I have 4 on the left and 2 on the right, which means that I need to raise the number of carbon on the right side. On this one, I already tried 2, and obviously that's not giving me enough to match the left, so I need to raise that more. I can't do 3 because that'll give me an odd number of carbon atoms. I want it to be 4, so let's go ahead and try a 4 coefficient in front of CO2 and see how this affects our counts. So now 4 times 1 carbon atom will give me a total of 4 carbon atoms. And now remember this 4 also applies to the oxygens. Now I take 4 times 2 oxygen will give me 8 oxygen on this CO2 molecule, plus the oxygen from water, which is 2 times 1 2, so that's 8 plus 2 gives me a total of 10 oxygen on my right side. So now comparing my elements from left to right again, I have 4 carbon on the left, 4 carbon on the right. That's good. 4 hydrogen on left, 4 hydrogen on right. That's good again. And now my oxygen, I have 2 on the left and 10 on the right. This is the one that's not out of balance. So now, because I have more oxygen on the right side, I need to raise my oxygen count on the left. And here's my oxygen compound on the left for the reactants. It's just O2, so I need to multiply O2 by some number to give me a total of 10. So that number that will go on there is 5, because 5 times 2 will give me a result of 10 on this. All right, so now we can take a new count of all the different elements, and we can see that carbon, they have 4 on the left, 4 on the right, that one's matching. Hydrogen, 4 on left and 4 on right, that's matching. And oxygen is 10 on left, 10 on right, again, that's matching. So because I have the same number of atoms on the left side than I do on the right side, this is finally a balanced chemical equation. And the coefficients that are needed for this is 2 moles of C2H2, 5 moles of O2, and when those two react together, they will form 4 moles of CO2 and 2 moles of H2O. And so this last step that I want to show you is just the thing that I did last, is that it's really more of a tip for these types of problems, is that when you can see a chemical equation and you can see that there's a single element on either side of the equation, you want to save that for the end, because that is the easiest group to change without affecting your other counts. You saw that in this problem, I had to go back and forth between both sides of the equation, just changing one element at a time, because when I raised the number of the coefficient on CO2, I changed both carbon and oxygen, and so I had to do a lot of balancing back and forth on that. When you find a single element compound on either side of the reaction and you leave that until the end, it's very simple to just change the coefficient of it without changing your other elements on it. So that's why I really recommend saving that until the end. All right, but on that's the basics of balancing chemical equations. So make sure you use this information to practice up on some problems, because I know this seems like a very long process, but it gets better with time, it gets better with practice, and just being able to more directly jump to a balanced equation and seeing the connections between both sides of the reactants and the products.